All right, so sigma notation. Y'all have seen this before. Just to point out a couple of things, this little I right here is called the index of summation. It's a dummy variable. It's just taking the place of something. A sub I is whatever I is. Like if I is 5, then A sub I would be the fifth term in that sum. So remember, we're adding things here. It gets more complex than that, but we're just basically adding stuff. That's what that summation notation means. So this one is saying I starts at 1, that's this bottom number right here, and goes to n. Now sometimes they'll give you n as an actual number. Sometimes it'll just be n, and when we start taking the limits of these things, it'll just be n. So we're going to combine limits in here too. This is something that you might want to go back and look at again. It's a little strange the first time you see it. Okay, so let's look at some examples. If you look at A, that's saying we're starting at 1 and going to 6. And so notice what's happening. Each one of those numbers from 1 to 6 is taking the place of I. I is just a placeholder. Look at B. Is the sum going to be any different there? But what changed? We started I at 0. We put I plus 1. And then we stopped at 5.
Oh, yeah.
So there's two different ways of writing the same result. Look at C. If that doesn't make sense, say something.
You drew out.
Right. I is just a placeholder. D. Notice what's going on there.
Same basic idea.
Mm-hmm. Now,
I've got the names of those things, but it's kind of like the multiplication, the addition version of those statistics thing. We'll put the exclamation.
Yeah, exactly. Look at E. Notice the 1 over n. I could pull that 1 over n out front. I don't have to put it with each term. I could pull it out front and multiply it times the end result if I wanted to. Mm-hmm. Well, n's not a variable. Once you know what n is, once n is locked in, it's a constant. But yeah. Look at F. Here's a little foreshadowing. We're talking about areas there. Yeah, that delta x means what's the change in x. So we're going to see that in just a second. Look down here at the bottom. This sort of reiterates what I said. If you've got a constant, and down here k is a constant, rather than make it part of each little sum as we're going along, you can just pull it out front.
That makes sense.
Notice something about 2. It's saying if you've got some a sub I plus or minus a b sub I.
So going back to
just one second. If you've got that, then you can split them apart and sum them separately. Okay, what?
So going back to E, even though n is on the top part of the sum, it's still a constant, so you can pull it out and just worry about the k.
In that context, yeah. Okay, we're good so far. Okay, here's a few other little formulas. Now then, look at these. The first one's saying if you're just adding up a bunch of constants, or the same constant over and over and over again. Look at number 1. What if C was 10? And that says, starting at 1, go n times, just adding 10 each time. Well, isn't that just n times 10? I mean, really. Pretty much. 2 is going to come in handy, because if I'm summing up I, you go, well, that's easy. It is if n is 10, but what if n is 1,000? Do you really want to add up 1 plus 2 plus 3 plus 4 plus 5 all the way up to 1,000. And this gives you a shortcut. On 2, if n were 1,000, what would this be right here? It'd be 1,000 times 1,001 divided by 2. And that'll be your sum of the values 1 through 1,000. I squared would be even worse if you're doing it by hand.
How would that be the sum of 1 to 1,000 when that's the last of 1,999 prior values?
Somebody worked these out. I didn't.
It's not.
But these have been around. You've got 1,000 times 1,001, so that's over 1,000,000 right there. Divided by 2, so that there's going to be over 500,000 of those things. I square, look at that thing. N times n plus 1 times 2n plus 1.
I'm understanding. Sorry.
Okay.
I didn't realize these were.
These are shortcuts.
Yeah.
These are lifesavers. Look at 4. That's dealing with I cubed. And notice the relationship of 4 to 2. It's kind of strange. If you took 2's pattern and squared each thing there, you get the pattern for I cubed. All right. Let's evaluate these. Now then, we're going to put some of those shortcuts and rules into practice here. I've got the sum starting at 1 going to n. And they want us to do this for 10, 100, and 1,000 for n. All right, looking at it, one thing I can see is I can rewrite it like this, can I? Just the first part. I can pull that 1 over n squared out because I know n is going to be a constant. And then what's left? Well, I've got this, I plus 1. I'm looking at the I plus 1 and I'm seeing, okay, I'm adding some things together. That means I can split them apart. So I could write it like this. I'm splitting the 1 apart from the I. I'm going to treat them differently. So right here, I'm using those shortcuts. If I'm summing I from 1 to n, then that's going to be the n times n plus 1 over 2. And if I'm summing 1 n times, then that's just going to be n. Okay, so far I haven't introduced any of the 10 or 100 or 1,000. I'm going to get kind of a general solution here where we can just plug those things in. So, work it a little bit more here. Okay, so then I can cancel. Which you might have said this. Well, I've got n plus 1 over 2n.
I didn't cancel. This is the first one, the second part is 1 over n.
And on my second term, I've just got 1 over n. Now that's pretty simplified. But if I wanted to take it a little further, I could do this. Right, and put both of them over 2n. Again, the hardest thing about calculus to me is the algebra. And that's going to give us this. Now we can plug the 10 in, the 100 in, the 1,000 in. And so when I put a 10 in there, I'm going to get 13 over 20. I'm just plugging 10 into that last equation up there, the n plus 3 over 2n. And when I plug 100 in, I'm going to get something similar. And when I plug 1,000 in, I'm getting that. Okay, we good?
So what's the difference between n and I again?
I is a placeholder. It's a dummy variable that
I is the start.
that's your iteration.
I is the start point, n is the end point.
Yeah. Well, whatever I starts at, yeah. But I is just a placeholder for the values of those a sub i's, basically, that we looked at. Looking at b, think about it for just a second. I'm going from I equals 1 to n, but I've got a constant times I squared, and then I've got a subtraction multiplied times 2i. So we can use those shortcuts to really help us here. If you were trying to figure this out any other way without those shortcuts, it wouldn't work. So I'm going to pull the 3 out, and I'm going to pull the 2 out of the minus 2i part. Okay, so I've split them into two different summations, if you will.
I'm not looking forward to what happens, but I does not equal one of these.
All right, so then I just do a little house cleaning here. For the first part, the I square part, I plug in its shortcut. All right, so it's going to take a minute here. Next thing I can do is cancel. So I've got n times n plus 1 times 2n plus 1 over 2. And then my second term out there is just going to be n times n plus 1. And then because I like to pull common things out, I'm going to do that in a second. So I'm going to get them. That's basically what I just said. All right, so then I can put all of these over one denominator, like this. Multiplying the second term by 2 would do that. Now I just start simplifying. I pull the common thing out, do this. So the n and n plus 1 are common to both those terms. That's just the way my mind works. You don't have to do that, certainly. And I'm getting this then. And so now I'm going to stop right there. If I wanted to plug 10 in there, then it'd be what? 10 times 11 times 19 over 2. That would make it pretty easy. Getting the general form, I only had to work it once doing the long way. If you did each of those the long way, it's going to take you forever.
Exponential. Would it be exponential? No, it would be exponential.
It'd just be a pain. Okay, question so far. Look what we did. We combined several different rules and shortcuts there. You might be wondering, what's this got to do with calculus?
Honestly, this is making sense. I kind of wanted to keep it that way.
Well, you're going to get your wish a little longer. Okay, so then we're just looking at the notes. So they're correcting us on our misuse of the language there. So from this definition of how to get the area of a rectangle, and you all have probably done this in geometry, and you could get the area of a polygon just by splitting it up into triangles, as long as you can know the base and height of those triangles.
I don't remember, but now that you mentioned it,
It's not a life-changing thing. But you could do that, right? As long as you're talking about a polygon, you can split it into triangles And as long as you know the base and height of each one of those triangles, you're good. And for regular polygons, that's not that bad because you've got central angles and things like the hexagon there. But as it points out at the bottom, if you're talking about something that's not a polygon, finding an area could get a little more interesting.
Yeah, you'd have to split things, or you
Well,
can't really split things up into circles, can you?
No, and so here's what they did. That leads right into this. If you go back all the way to Archimedes, who was a pretty heavy hitter in his own right, what they tried to do to get the area of a circle before they figured out the pi r square thing was they would inscribe a polygon inside the circle and then circumscribe a polygon outside the circle. And then if you look at those two pictures, the one that's circumscribed, the area of that thing would be a little bit bigger than the area of a circle. The one that's inscribed, the area would be a little bit smaller. And so as they kept adding sides, they got closer and closer and closer to the actual area of a circle just by experiment.
And that's limits.
That's limits before they even called them that. And in computer science, I would have people write programs that did these equations for the polygons and just let a computer figure it out. And as you get closer and closer and closer, you would approach the actual area of the circle. And then it tells us at the bottom, we can use this to approximate the area under a curve. Now, up to now in your math careers, you haven't done that. That's what all this is leading us to. So take a look at this one. They've divided, we've got a curve going from, 1 to 2? 0 to 2, sorry. And they've put 5 rectangles inscribed in that part of the function. They're telling us f of x is negative x squared plus 5. Okay, there's the part of that curve from 0 to 2. So they have divided, look what they did. They took the distance from 0 to 2 and split it into 5 equal parts. So each thing down there on the x-axis is 2/5. Now I'm not trying to go too fast here because this is going to require some thought. So we've got an inscribed set of rectangles. On the right, we've got a circumscribed set of rectangles. Now, just like with the circle, the areas of the rectangles under that curve, that total area is going to be less than the actual area under the curve. The ones on the right, the area of those rectangles is going to be slightly higher. And we want to find 2 approximations of the area, sort of like they did with the circle. So keep in mind that each rectangle, the area is some value f of x for that little part. And we're using the right-hand corner up there of that rectangle. It's whatever f of x is, that's your y value, in other words, times delta x. Well, delta x is the same all the way across there. Delta x is 2 over 5. Y'all with me? The change in x is 2/5 each time. Okay, so with that thought in mind, we can sum up those areas. Now look what's going on. This says, find out what f of each little subpart, each little rectangular base is. Find f for that x sub I. And then multiply it times delta x. That's going to be the area of a rectangle. Well, what does that translate to for this problem? Give it a second here. Notice inside the parentheses, we're going from 1 to 5, our summation. I is standing for what? I is starting at 1. So when I is 1, we're saying 2/5. We're using the right endpoint. We're using this endpoint right here for our rectangle. When I is 1. When I is 2, we're using this endpoint, and so on. So I is a placeholder, but it's helping us do the math here. So I've got, what would f of that be? Well, it'd be 2/5 I, all of that squared. Why? Because it says minus x squared up there is our f of x, plus 5. Here's where it starts getting a little more strange. So now what am I going to do? Okay.
Are we gonna split it up?
We are. We are. So let's do some math here. Oh yeah, there's my delta x. I don't want to forget it. Our delta x is 2/5. And that's a constant. Okay, so let's keep working on it. So I go ahead and square what's inside the parentheses there. And I'm getting 4/25, that's negative, 4/25 I square. The 5, notice, is not being squared. The 5 is that constant being added to the rest of f of x there. Now I'm looking at that and I'm seeing, okay, I've got negative 4/25 I squared. And I've got 2/5 multiplied times everything inside there. So I can do this, can I? So I'm in the black, 2/5, I'm multiplying the numerator times the 4 numerator and the 5 denominator times the 25. Keeping the negative sign. And if I multiply 5 times 2/5, I just get 2. So this is getting simpler. In bigger college classes, a lot of people decide at this point that they really don't want to be engineers. You know, they might want to rethink it.
I get it.
Good, good.
I think.
Y'all are not the average group. All right, so I can pull the constant out. And notice it's a negative. And I can split my summations. It just got a whole lot simpler.
Did you add the 2/5 initially because of the achievement?
Adding the 2/5.
Yeah, like when you multiplied it.
Yes.
I'd multiplied 2/5 times 5. Is that what you're talking about?
She's talking about why is the 2/5 there in the first place? And it's because it's the change.
That's the delta x.
Yeah.
That's the base of the rectangle, as it were, of each rectangle.
Either it simplifies it down into something surprisingly simple, or the answer is just as complicated as the question.
Well, let's see. Life is an adventure. Let's do this. Now, for my I square, I know what n is, don't I? Yeah, n is 5. So the shortcut for I square is n times n plus 1 times 2n plus 1. So that gives me 5 times 6 times 11 over 6. Now it's just math. And the summation of I going from 1 to 5 of 2 is just 5 times 2, which is my 10. I can cancel some things here. On the top, I've got negative 88. On the bottom, I've got 25. You're welcome. I'm glad you were here. So this just got a whole lot simpler. I can put everything over the same denominator. Which gives me that, which if I really wanted a decimal answer, comes out to be about 6.48. Now, what does that 6.48, or the 162 over 25, what does that represent? Not the area, it's the inscribed area. We just used one set of rectangles there. That's this part. We still have to do it again for the second part over here on the right. And then we know what? When we do that, we'll know that the true area of that curve from 0 to 2 is in between those two amounts.
So why did you, in your first thing, when you plugged in the values, why did you use 2/5 for x?
Because that was this right here. Each one of those is going to be 2/5 times I.
Okay.
So
So what's the difference between the change in x and the x then?
the change in x is the width of the bases. It stays constant.
But doesn't from 0 to the first one stay constant too?
Yeah, but what if I'm talking about this right here? See, that's not 2/5 anymore. It's 3 times 2/5. That's a good question. Good question. And so now then we got to do the same thing for the other side. And we're not going to go all the way through it because it's going to be similar, but I do want to point out something. Here's how I have to start it off. And if you look back, you'll see that that's different from the way we started the left-hand side off. Why? Because now I'm talking about these. There's my first one. Here's my second one. We're using the left-hand corner at the top of the rectangle. So over here I've got to say I minus 1. Because I want to start at 0. So when I is 1, then that'll be f of 0. Does that make sense? And so I've got to trail behind all the way across. And so then I'm just going to do a little bit of this. There's my delta x. And so I skipped some steps here. They're going to be very similar to what we did at first. But notice what's being squared. The I minus 1 is being squared along with the 2/5. Okay, I can pull this becomes very similar to what we did at first, but look at what I've got. I've got I squared minus 2i plus 1. That's from squaring I minus 1. And then I'm going to sum up the 2 out here also. Okay, look at it, see if it makes sense. If it doesn't, let's talk about it in a minute. Notice it changed what's in blue inside the brackets. So now I've got what? I'm going to split the blue part into 3 separate summations. And so similar to what we did the first time, the shortcut for I squared is that. N times n plus 1 times 2n plus 1. That's just for the I squared. For the minus 2i, here's my shortcut. For the 1, it's just that. And that gets everything in blue, but I've got that summation from 1 to 5 of 2 out there also. So there it is. And we can stop right there, if that makes sense. There's no need working it all the way out. We know it's going to be bigger than the number we got the first time. And so we'll know that the area under the curve itself is going to be between those two values. There's a lot of logic involved in this. And again, going back and watching this might not hurt. I was pretty rusty on it. It's all leading to something though, and we're not quite there yet. Okay, so let's look at this curve. Notice there's a point A and a point B on the x-axis. I want the area of that curve, the area under the curve between A and B. So it's got some boundaries, the x-axis, x equals A and x equals B. Look what we're doing. We're taking the right endpoint, B, subtracting A, the left endpoint from it. That's going to give us the distance in between there along the x-axis, and we're dividing by n. That's going to be what? Our delta x. That's what we did the first time. Going from 0 to 2, they gave us, delta x was 2/5. And I drew a green circle around it just to remind you that delta x is the base of different rectangles under there. Okay? This is telling us in each little sub-interval that forms a rectangle, there's going to be a minimum and maximum value. Both of them in there because of the extreme value theorem. So if we get all the minimum values and all the maximum values and find the areas based on those values, we've got what I circle in green down here. The function applied to the minimum values times delta x is going to give us the area of the inscribed rectangles, and something similar for the maximum values of f of x. And they're given a name, the lower sum and the upper sum. Here it is in a slightly neater form. And the last sentence on this page says, the more rectangles you make, the more accurate this estimate becomes. So instead of using 5 rectangles, what if we'd used 100 in that first example? Well, then it'd be very close. All right, so we're doing the same kind of thing that we did with that first example. We've got inscribed rectangles. We've got circumscribed rectangles. We know the true area bounded by x equals A, x equals B, and the x-axis is in between those two sums. And the key word there is sums. The concept is easy. The practice can get kind of interesting. So let's do one. I want to find the upper and lower sums for these, what's the same curve, f of x is x squared. And we're going from 0 to 2. All right, the first thing I do is I say the right-hand side minus the left-hand side on the x-axis, I get 2, which means delta x is going to be 2 divided by, now we're not coming up with a certain number of rectangles. This is a general case. So I'm just putting n there. The more n, the bigger n is, the smaller delta x gets, right? If n were 1,000, we'd be talking about 1,000 little rectangles. Okay, next thing I do, I'm getting the lower sum. And one way of notating is like this. The function of the minimums times delta x, the summation of all of that, is going to be our lower sum. So let's translate it to our actual function here. And look what I'm having to do again. The lower sum, I'm using the left-hand side of the inscribed rectangles. That's why it has to be I minus 1. And so I've got 2 over n is my delta x. So that very similar to the first one at this point, the 2 over n in black is our delta x. Well, I'm seeing a couple of constants I can pull out. If I'm going too fast, holler. So I'm using my shortcuts again. It helps if you memorize those. So the shortcut for I squared is that n times n plus 1 times 2n plus 1 over 6, and so on. Now what happens at this point? You do a whole lot of multiplying of polynomials, and I did that for you. All of that. If I multiplied 8 over n cubed times all of that stuff and reduced it, here's what I'm going to get. 8/3 minus 4 over n plus 4 over 3n squared. That's for the inscribed part. For the circumscribed part, I would have to do the same thing. What would change? That I minus 1 would just be I, because we're using the right-hand corner of the rectangles. And I did that, so we don't have to work all the way through that. Here's what I got. For the upper sum, I got this. What's the difference? There's one, there is minus 4 over n, and the upper sum is plus 4 over n. Now think about this. Think about this. What if I stuck limits on those? In fact, let's do this. There's my lower sum, there's my upper sum. I just gave us a little more room here. What if we stuck limits on it like this? For the one in black, for the lower sum, what's the limit as n approaches infinity? 8/3. What is it for the upper sum?
8/3.
What do we know the area is then? 8/3. The area under that curve is 8/3. Now we're going to find a more streamlined way of figuring that out, but this is just getting you in the frame of mind. Okay, we're taking rectangles, we're doing this, limit applied to that sum, and that leads us to one more little conclusion here, I think, or maybe a couple. Here's the formal part of it. If you go back to here, we've got a lower sum and an upper sum. The limits of both of those are the same. That means the area of below the curve is being squeezed in between them, and so equals their limits, because their limits are the same. Look at the important part that this is saying, though. Look at the last little paragraph. I can choose any x inside each interval to find the limit. It doesn't have to be the right-hand corner or the left-hand corner. It could be the midpoint of each little rectangle. I'll let you read that. So we want to find the true area here. Now I don't have to use I minus 1 or I, I'm just going to use I. So what do? We're going from 0 to 1. So I subtract A from B, get 1. I can do that even. And so that means delta x is going to be 1 divided by the number of rectangles. You see a pattern developing here. So I'm going to just start off with visualizing this as a limit. Similar to what we've done before. Each rectangle, whatever point I pick in there, which is just going to be I itself, thanks to the theorems we saw on the previous page, it's going to make it easy. I put it in the context of our function here. Now our function is f of x is x cubed. So look what I'm doing. I'm taking every little I n and cubing it. And then my base is 1 over n, my delta x. And I is changing from 1 to 2 to 3 to 4 to 5 to 6, all the way up to, it's going to approach infinity. Do we have any constants? So I go ahead and cube this so we can see what's going on. So I've got 1 over n cubed and 1 over n, and they're being multiplied. Those are constants.
So would it be 1 over n to the fourth?
Yep. And so I can pull that out. I just put an extra step in there. So I can pull that out and get this. Now y'all, we're finding the actual area here, not an approximation. This is cool stuff, in my humble opinion. Okay, so now then, what am I going to do? I've got a shortcut for I cubed. And it's this. And some of you might be thinking ahead. Some of you, there's 2 of you right now. You might be thinking ahead. I can cancel some stuff. And on top, I've got n plus 1 squared. And on the bottom, I've got 4n squared. One more step, and I think you'll see what's going on here. If I had given you that problem right there, that last part, and said, what's the limit as n is approaching infinity? What would you tell me? 1/4. And that's exactly what it is. Now we can work it out, but you're exactly right, 1/4. You can, split the numerator, you can go through all of this, or you can recognize back there, like London did, that's just going to be 1/4 because those other terms are going to go to 0. For this reason right here. If you didn't catch that and you went ahead and simplified it, at this point you can see, okay, as n's going to infinity, I've got 1 divided by infinity, 1 divided by, so those are going to be 0. So our area just becomes 1/4. Not something I would have guessed, right? So we found the true area under the curve. We're going to talk about, like I said, better ways of doing that than this long roundabout way. But this is sort of the equivalent of the difference quotient in getting derivatives. This is leading us to, how do we really find the area on the curve where it doesn't take us a year to do it? And that's pretty much it for 4.2. And that's going to lead us to 4.3, but we'll worry about that tomorrow.